Today's busy shipping lanes present the constant risk of a collision at sea. As a plotter or a Sea Guard reporter, it's your responsibility to calculate fast, accurate information that can be relayed to the officer of the watch and used to perform basic maneuvers, such as evading or intercepting other ships. To do this, you must thoroughly understand the nature of relative velocity, the 6 factors that determine its value, and how to quickly calculate relative velocity information for any likely scenario.
Range.
Velocity and speed are often thought to be the same thing. In fact, they're not. Speed is the measurement of distance over time. Velocity is the measurement of distance over time in a specific direction. Relative velocity, then, is velocity measured between 2 objects when one or both is moving. To plot relative velocities at sea, you'll use what is known as the PPI presentation method. The PPI, or Plan Position Indicator, is part of the radar display. It's a transparent screen fitted over the radar display so that the radar operator can plot the movements of contacts on the transparency using a grease pencil. When looking at it, your own ship is always in the center. Everything else moves in relation to you. The PPI presentation method makes use of a maneuvering board to solve relative velocity problems. The maneuvering board is simply a paper representation of the PPI display. It will help you to visualize ships' maneuvers as they would be seen from the air. More importantly, it will let you plot ships' movements diagrammatically. The maneuvering board is dominated by what appears to be a spider's web. This is called a graticule. The graticule is divided into 360 equal sections. Each section represents 1 degree of the circle. The graticule is divided into 10 equally spaced concentric circles, which represent ranges. On the maneuvering board, there are 5 scales ranging from 1:1 to 5:1 inclusive. Choose the scale that's most convenient when solving a particular problem. 2 additional sets of scales are located at the bottom of the board. These are the logarithmic time, speed, and distance scales, and the 3-scale nomograms. These 2 separate sets of scales provide you with an easy way to determine speed, time, and distance. Given any 2 of speed, time, or distance, you can easily find the value of the other. You'll see how all of these scales work a little later. There are 6 factors or variables that affect relative velocity. These are your own ship's course and speed, the other ship's course and speed, and the other ship's course and speed relative to your ship. If any 4 factors are known in any combination, you'll be able to calculate the relative velocity. This is done by plotting ships' movements to create what is known as a RELVEL triangle. The following examples will show you how to use speed triangles to solve the 4 basic types of relative velocity problems. The first of these is called a closest point of approach problem. A radar contact is gained bearing 030 degrees at 12 miles. The contact's course is 220 degrees at a speed of 12 knots. Your own ship's course is 340 degrees at a speed of 13 knots. The officer of the watch will need to know where and when the closest point of approach, or CPA, will occur. Begin by selecting the most convenient scale for solving the problem. In this case, the 2:1 scale is best. Plot the information on the maneuvering board, starting with the position of the contact. Lay off the contact's course and speed vector, as shown here. Label this vector with a double arrowhead. A double arrowhead always denotes the target ship's course and speed vector. Now lay off your own ship's course and speed vector. Label this vector with a single arrowhead. A single arrowhead always labels your own ship's vector. To complete the triangle, simply link the ends of the two vectors that you've drawn. This line is the relative vector. The relative vector is labeled with an encircled arrowhead. To ensure the information has been plotted correctly, there are three important rules to follow. These are called rules of the arrows. The first rule is own ship chases relative. The second, enemy and relative converge. And the third, own ship and enemy diverge. When you've determined the information has been plotted correctly, resume your calculations. Using your parallel ruler, transpose the relative line on your triangle to the contact's position. Extend the line in the same direction that the arrow indicates. To determine the closest point of approach of the contact, draw a perpendicular to this relative line from the center of the maneuvering board. A 90-degree angle will be formed when the relative line is cut by the perpendicular. The intersection is the CPA. Now you have part of the answer to the problem. The contact CPA is 0.99 degrees at 4.4 miles. You still have to calculate the time at which the CPA will occur. To determine the time, you first measure the length of the relative line on the speed triangle. This will give the relative speed, in this case, 21.5 knots. Next, determine the relative distance the contact will travel before it reaches the CPA. In this case, 11.3 miles. Now that you have speed and distance, you can determine time using the logarithmic scale. The answer is 32 minutes. Your report to the officer of the watch is contact CPA 099, range 4.4 miles, time 32 minutes. Now let's look at a routine problem that you'll be required to solve when at sea, solving for an intercept. This is also called closing on a steady bearing. In this type of problem, you're required to find the course to steer at a predetermined speed to make a contact close the center of the PPI, or maneuvering board. A radar contact is gained bearing 090 degrees at 12 miles. The contact's course is 180, and his speed is 15 knots. You are to intercept this contact at a speed of 20 knots. The officer of the watch will need to know what course to steer and how long the maneuver will take. Using the 2-to-1 scale, the first step is to plot the contact's position. Lay off the contact's course and speed vector using the double arrowheads. From the contact's position, draw a line to the center of the maneuvering board. This line is the relative track. Label this line as the relative track by adding a single encircled arrowhead. Using your parallel ruler, transpose the relative track to the end of the enemy's course and speed vector. To ensure the information has been plotted correctly, apply the following rule of the arrows. Enemy and relative converge. Next, since you're required to complete this maneuver at 20 knots, mark the point where the relative line intersects 20 knots. This will give you the course you must steer at 20 knots to make the contact close the center of the maneuvering board. Remember, the single arrowhead labels your own ship's course and speed vector. The course to steer is 139 degrees. Next, determine how long it will take to complete the intercept. To determine relative speed, place your dividers at each point of the relative line on the speed triangle. The relative speed is 13 knots. Knowing that the relative distance is 12 miles and the relative speed is 13 knots, we can use the logarithmic scale to find out how long it will take to complete the maneuver. In this case, 55 minutes. Your report to the officer of the watch is course to steer 139 at 20 knots, time 55 minutes. Now let's look at the opposite problem. Opening on a steady bearing. In this type of problem, you want to see a contact open away from the center of the PPI or maneuvering board. The relative track will always point towards the edge of the maneuvering board. A radar contact is gained bearing 090 degrees at 6 miles. The target's course is 020 degrees at a speed of 14 knots. You're ordered to open this contact on a steady bearing to a range of 12 miles at a speed of 18 knots. The officer of the watch will need to know what course to steer and how long the maneuver will take. Using the 2-to-1 scale, plot the contact's position. Lay off the contact's course and speed vector with double arrowheads. Plot the intended position of the contact, in this case, 090 at 12 miles. Draw a line between the contact's present position and his intended position. This is the relative line. Label it with an encircled arrowhead pointing toward the edge of the maneuvering board. Transpose the relative line to the end of the contact's course and speed vector. Since you're required to complete this maneuver at 18 knots, mark the point where the relative line intersects 18 knots. From the center of the maneuvering board, draw a line to the point where 18 cuts the relative line. Label it with a single arrowhead. To ensure the information has been plotted correctly, apply the following rule of the arrows. Own ship and enemy diverge. The course to steer in order to open on a steady bearing is 317. To calculate how long this maneuver is going to take, place your dividers at each point of the relative line on the speed triangle. This will give you a relative speed of 16.8 knots. In this problem, the contact must travel 6 miles. Using the logarithmic scale, you'll find that it will take 21.9 minutes to complete the maneuver. Your report to the officer of the watch will be course to steer 317 degrees, time 21.9 minutes. Now let's look at the fourth and final problem. Calculating true wind from relative wind. Wind direction is always given as coming from a particular direction. But when it's plotted, it's done going to a certain direction in order to conform with the speed triangle. This applies to true wind and relative wind. The length of the relative vector is determined by the relative wind speed. Your course is 045 degrees at 15 knots. The relative wind is from green 45 at 17 knots. To calculate the true wind speed and direction, use the 2-to-1 scale to plot the information. Lay off your course and speed vector and label it with a single arrowhead. Plot the relative wind coming from green 45 and label with an encircled arrowhead pointing toward the center of the maneuvering board. Transpose this relative wind vector to the end of your course and speed vector. You'll have formed an angle of 45 degrees. Ensure that you plot the relative wind going to and label the vector as being the relative line on your speed triangle. Identify it with an encircled arrowhead. Set your dividers for 17 knots, this being the relative wind speed. It will determine the length of the relative vector of your triangle. Place one end of the dividers at the end of your own ship's vector, and where the other end rests along the relative line, mark this point lightly. From the center of the maneuvering board to where the relative line of your triangle was cut, lay off the true wind course and speed vector. The speed is again determined by the length of this vector. In this problem, the true wind speed is to 329 degrees at 12.5 knots. Since you must quote the true wind as coming from, take the reciprocal bearing. You find the true wind is from 149 at 12.5 knots. Your report to the officer of the watch will be true wind is from 149 at 12.5 knots. The four basic exercises we've demonstrated in this video form the basis of all the RELVEL problems you'll be expected to calculate. Once again, they are closest point of approach, closing on a steady bearing, opening on a steady bearing, and true wind from relative wind. It's important to learn and understand the rules of the arrows. Remember, own ship chases relative, enemy and relative converge, and own ship and enemy diverge.